you for the invitation. I'm very happy to be able to talk about this research. And so this is kind of like it's based on several papers, so it's kind of like an ongoing collaboration. But so the topics I'm going to talk today are related to work with these four collaborators: so Pavel Exner, Hiroshi Sasaki, Matti Lassas, and Jinpeng Lu. And I'm going to base it on these papers. So two of them have already been published last year, and then the fourth one is more about like scattering. It's been submitted and accepted. So first I'm going to talk a bit more generally about the spectral problem and maybe the continuous case, and then I will talk about graphs. So the inverse spectral problem can be said in one sentence in a way. So if you ask, like, can one hear the shape of a drum? So that's what Mark Kacht asked like in 1966. And the idea there is that when you hit on the drum, the surface will start vibrating. And if you model this situation so that the shape of the drum is like a two-dimensional region, then you can kind of model this vibration by eigenfunctions of the Laplacian. So Laplacian of u is equal to 0, or if it's the eigenfunction, Laplacian of u is equal to lambda times u, and then u is equal to 0 on the boundary, meaning that it's like a fixed, or could be Neumann condition, kind of depending on how it is and so on. But anyway, then the eigenvalues will somehow physically, you can use them to describe the kind of sound you will hear from that. And the answer to this question, so if you're given the eigenvalues of this kind of Laplacian, and you ask, can you determine the shape of the vibrating region? The answer, unfortunately, turns out to be no. So Gordon, Webb, and Wolpert in '92 constructed this kind of two regions which have different shapes. So here the extremity here is a square, and here the extremity is a triangle. So they're different shapes, but turns out that they have exactly the same eigenvalues for the Laplacian. So the answer is no. And one could then ask, okay, is this the end of inverse spectral theory? But we can then, as we usually do, is we add more data. So then the next question is, okay, what if we, in addition to knowing the eigenvalues, we also know how the eigenfunctions behave near the boundary? So if you have, let's say, Dirichlet eigenfunctions, you know that their value is 0 on the boundary, but then you give extra information like their Neumann data. So what is the normal derivative of each of those functions at each point on the boundary? And then you can ask the same question: does that determine the shape? And you can talk about this, let's say, on like domains on Euclidean planes or spaces, but it's often also quite interesting to ask it for more complicated topological structures. So if you are considering like the Laplacian and you want to consider like continuous case, you can ask this for manifolds with boundary. And then it becomes interesting to see like how holes and other things affect these eigenvalues. So in those situations, you say like, okay, let M be a Riemannian manifold, and it has to have a boundary, and then it has a metric G. And then the PDE would be given by this Laplacian, which in local coordinates can be defined in this way, but that's the geometrical Laplacian. And once this operator is defined, again, if you have like a local chart, so in local coordinates, you can like pointwise form this eigenvalue equation. So you look at minus Laplacian of G, plus maybe some potential. For example, if you're interested not just in the geometrical shape, but on some like functions on it. So you take this as an operator and look at the eigenvalue problem. So phi j is an eigenfunction for this if it satisfies this first equation with lambda j as the eigenvalue. And if you're, let's say, interested in the Neumann problem, then you impose the boundary condition that the normal direction on the boundary of each of these phi j's is equal to 0. And then the question is, suppose we are given this, we're given the boundary, and we're also given the eigen values, and then the restriction to the boundary of the eigenfunctions themselves. And we're given this for the whole sequence of all possible eigenfunctions, all eigenvalues, eigenfunctions. Does this then determine the manifold, and does it determine maybe this unknown potential if it's like non-zero, for example? And I'm kind of not going to give a big answer to this. So there's a situation where it's known, there's a situation where it's not known, but I'm kind of going to skip over this past literature. Because the work that I was doing on is like this kind of situation with weighted graphs. So we're considering actually discrete graphs. So you think of it like a collection of points. They can be embedded in some space, or they can be completely like abstract points. But in these pictures, I denote them, embedded on the slide, so it's like embedded in 2 dimensions. So we have the points, and the points will be partitioned into 2 sets. So one is G for graph, and then there's another one B for boundary. So we call G like the interior nodes, and then B we call the boundary nodes, and we often denote it as partial of G, like for manifolds when you talk about the boundary of a manifold. So that's just the points, and in addition you have the set of edges, and it's just a connection between 2 different points. And then once you have your set of points and the edges between them, you can define 2 types of functions. Like if you're interested in not just the topology, but also maybe some physical functions on them. So you can define different types of weight. So you have like the edge weight, which here is denoted by G, and then there's X and Y for saying that it goes from point X to point Y. So it's on the edge. And then there is mu, which is a weight on one of the vertices, one of the nodes. So this has just 1 point here on the subindex. So this is kind of the type of graphs we're considering in this work. And then once that is done, we would also like to have the Laplacian. So given some function that's defined on all points of the graph, including the boundary, we can define the Laplacian for interior points. And if you ignore these weights for now, it would kind of be some kind of like sum of all the differences of this function along the connected points. So this means that we're looking at the sum of over all y which are connected to x with one jump in the network. And if then choosing suitable weights, you will get different type of Laplacians. For example, if some people do numerics, and let's say they have like a rectangular grid, they might do like a finite difference approximation of the continuous Laplacian. It will be represented by one of these discrete Laplacians. If you put, I think, both of them to 1 or something like that, or maybe here you will get the degree, meaning how many connections there is to x, then you will get so-called like a combinatorial Laplacian. But then in addition to that, you have to define what would correspond to this like normal derivative. And And it has pretty much the same formula. The difference is now that it's a bit of technical condition, but we usually think that the boundary is only connected to a single interior point. So you look at the boundary point, you look at, it can be connected to multiple ones, but there shouldn't be connection between boundary points. So you take your boundary point, look at which interior point it's connected to, and then kind of do this same logic, like you take this weighted sum of the differences of this function. Yeah, and okay. And one might wonder, okay, this is like this purely discrete thing. Does it have like any kind of like physical applications? And it has a relation to so-called quantum graphs. So quantum graphs, you don't just look at functions whose values are defined on the vertices. You have functions that are like defined also on the edges. So here, for example, this u subscript is a function defined on every single edge. And you identify an edge with a segment. And since it's a segment and a function defined there, you can consider an ordinary differential equation or even partial differential equations if you take time into account. So you would have, for example, this kind of like Schrödinger equation here on each of the edges. You would have maybe u is equal to some given value on the graph boundary, which in this case means, sorry, it's like some set of vertices forms the boundary, and in those you have set u to be some given value. And then on all the interior vertices, so yeah, this is not all vertices, but all the interior vertices, you have some kind of like coupling condition, and this so-called delta coupling condition. So you have some constant for each vertex, CV, and you want the sum of like the derivative going from like outside from that particular vertex along each of the edges will be equal to the constant times the value at the vertex. So if CV is 0, for example, then this is this usual no sources condition, meaning that, you know, if you have, for example, like water waves in your network, there's no like sinks or sources. So if you look at this kind of like quantum graph situation, you can kind of you can kind of do some calculations, and you can reduce it to this kind of like more complicated looking thing. But if you further transform this a little bit, you will see that what you have here is going to be pretty much equal to one of those discrete Laplacians. What you have here is just going to be some function of v, and these equations will be true on all the interior vertices. And then on the boundary vertices, you will have like u is equal to f. So in other words, you can, for this kind of quantum graph an equation on it, you can formulate a completely discrete version that kind of corresponds to it. And it turns out that if this u bar solves this continuous problem on the quantum graph, then this u without the bar solves this discrete equation. And then there's also vice versa. So if u without the bar solves this discrete equation with the Laplacian and the potential, and then you kind of on each segment form this u bar according to, you know, what the boundary value is going to be from the different like vertices you have from this u. You can see that then you have a solution to this continuous equation. So that's like one motivation. So you can get from these quantum graphs, which are more closer to physical system, into looking at these discrete graphs and kind of vice versa. So that was kind of a little bit of motivation. Let me then formulate the spectral problem. So we are given a discrete graph. So there's the interior nodes, the boundary nodes and then the set of edges. And then there's the two weights, G for the edge weight and mu for the vertex weight. And then you can also have a potential defined on the interior nodes. So that eigenvalue equation is just the following. So formally, it's kind of like in the continuous case. You have minus Laplacian plus Q, and then that's applies to some function phi j on the interior, and that is equal to eigenvalue times phi j on the interior. And then on the boundary, you just put that normal derivative of phi j is equal to 0. And then the inverse problem is given this boundary spectral data. So you are given this set of boundary points. In practice, you just have a number. You just know, like, okay, we have like 10 boundary points because it's an abstract graph. And then on each of those boundary points, you will know for each eigenvalue, the value of these eigenfunctions on each of those boundary points. And you know to which eigenvalue those correspond to. And because it's a finite graph, and this Laplacian is like self-adjoint and so on, you can do the basic spectral theory and see that, you know, there's going to be as many eigenfunction as there's going to be interior nodes. So then the question is that, can we determine, you know, the structure of the graph from this? Can we determine these coefficients, these weights, or this potential? And yeah, unfortunately, the answer is no. Like you cannot. So we were working on this together, and Jinpeng Lu found by just calculating graphs with like a few vertices. So he found this counterexample. So if you put weights constant 1 and no potential, then these two graphs where these empty circles are the boundary nodes. So these two have exactly the same boundary spectral data. So they have the same Neumann eigenvalues. And also, if you look at the normal derivative of each of the eigenfunctions, so in a sense, like the value here minus the value there, it's going to be the same for these two graphs. So the answer is no, you cannot solve the problem. Well, then you know, after that, we have to find, okay, under what circumstance can we solve it? And for that, I have to go more into this geometric informations. So we have to put a metric on the graph, and it is done in a standard way. So the text is you know, more complicated than what actually happens. We just say a distance from one point to another is the shortest amount of jumps you can go along these edges to get to it. So from this edge here, distance to here is just 2, because you go through 2 edges. That's like the shortest possible. And paths here, they're just like, well, they go through these edges, and then you don't like teleport around. So we use this. So we're kind of analyzing what happened with this counterexample that I'm showing here. And the problem here is in some way that there's like kind of too many boundary points, too many interior points compared to boundary points. And also these boundary points kind of don't really have good access to this part here or this other part here. So if we're comparing it, let's say, to the continuous case, in the continuous case, the boundary usually means that it has to like circle the interior in some sense. And that kind of doesn't happen if you just take arbitrary points as your boundary. So for that, we need to define something called the extreme points of a set. And I'm showing here with a continuous situation just so that it's easier. So given some set, and you know, the boundary of this whole universe, the boundary is here, the unit square, and the set is here in the interior. We say that some point on this set is an extreme point of this set with respect to the boundary. If on the boundary there is some point such that this point on the set is the unique closest point of this set. So for example, this point here cannot be an extreme point, because no matter which point you look at the boundary, there will be other points which are closer or same distance apart. But these two extreme points, you can think of them as the highest point and the lowest point. So if you take any like compact subset of this unit square, you will always find two extreme points, which like the top, one of the top points, one of the lowest points. And it turns out that if we formulate this condition in the discrete graph, it's going to be good enough for us to solve the inverse spectral problem. So we are going to look at graphs which satisfy this so-called two-point condition. So this first one is the two-point condition, and then the second one is like a technical thing with respect to the boundary. So we want that any subset of the interior of G that has at least 2 points has at least 2 extreme points, meaning that on the boundary of your whole network, you can find 2 points on the boundary. And if you start looking, what are the closest points of that set S, you will find a unique one. But the condition is not just for one set. It has to be true for any set with at least 2 points. So it's kind of difficult to check, because if you have n interior points, then you'll have like 2 to the power of n, pretty like more or less 2 to the power of n, like different sets that you have to check, like do they satisfy this condition. So this is the actual condition that's needed for solving this problem, at least using the way that we solved it. But it's very difficult to check in this form. I will talk about this a little bit later also. So in addition to that, we want that every boundary vertex is connected to only one interior vertex. But you can replace this in such a way that if some boundary vertex is connected to 2 interior vertex, then those 2 have to be connected to themselves. This is just to make it so that the waves cannot like go faster on the boundary than they can go on the interior once we define the wave equation later. So anyway, so this 2-point condition, and the other one is valid for trees. If we consider the leaves as boundary nodes, it's also valid for little perturbations of all the standard lattices. Like I've shown the hexagonal lattice in many cases, but like for triangular lattice, you require this other condition, like 2', the one I was saying. Like if there's 2 points connected to a boundary node, those 2 interior points have to be connected together. Right. Anyway, so once we have that 2-point condition, we were able to prove the solution to this inverse boundary spectral problem. So let's look at 2 of these kind of graphs. And also there's the weight functions, and there's also the potential functions. So first of all, we assume that the boundaries can be identified using a bijective map, meaning in a sense that they have the same number of boundary points, and they can be put in some correspondence. And then we also assume that using this correspondence, the boundary spectral data of these 2 graphs are the same, meaning that we can select the eigenfunctions in such a way that the boundary data, the boundary value of corresponding boundary points are the same for these 2 graphs. And then once we have those 2 things, we can solve the inverse problem. So we can firstly show that the topology is the same. So we can show that there's a bijection that goes all the way, to the interior and includes the boundary, such that if in this G graph there's a connection between the two vertices, then there's also a connection in the G prime graph and vice versa. So that means that they have the same topology. Again, due to technical things, I would like to give a brief comment that this phi does not necessarily extend this original bijective map. There can be some situation due to some symmetry that this phi can like have some permutations and so on. But it will certainly satisfy that these transmission eigenfunctions will, you know, have the same value on the corresponding points, even with this big phi. So that gives like, okay, the topology is fixed. So, okay, then if we use this phi to identify these two graphs, then we can show about these coefficients. So there's a lot of coefficients. There's the vertex coefficient, there's the edge coefficients, and then there's the potentials. So if we know that the vertex coefficients are the same, we can show that the edge coefficients are the same and the potentials are the same. If we know that the potentials are both 0, then we can show that these edge and vertex coefficients are both, you know, the same. We don't yet know if it's possible to show like all three are the same without doing some further assumptions. I think probably not. There might be some kind of transformations you can do. Okay. In other words, if you have these two graphs, you have this two-point condition, then the boundary spectral problem is solvable. And yeah, as I was saying, like to check if the boundary, if the two-point condition is satisfied. So that's going to take a lot of computations because you have to test something for every subset of 2 points or more. So it's too much to test. We can prove something similar to the continuous case. So we say that, so if a graph satisfies this kind of condition, so we can put some function h on the graph and also on the boundary, such that its value changes by at most 1 when you go from one point to another one through a single edge. And then we can, for this function h, we can calculate so-called forward gradient and backwards gradient, and it's going to be a set. So the forward gradient, which is denoted by n plus, so the forward gradient at some interior point x is all those points which are connected to x, where this function h has value 1 higher. And this backward gradient is those connected points where the function gets value 1 lower. So in the end, this function h is going to be like integer valued. And as you move through edges, you kind of want it to only like, you know, get like integer values. But what we want is with these forward and backward like gradients, we want them to be exactly 1 point. So we take any interior point in the network. That means there has to be exactly 1 point where you can go where the value of h grows by 1. Exactly 1 point where it decreases by 1. And all other points, the value of h stays the same. And then for boundary points, if you look at this n plus and n minus, they can stay the same or they can change by 1. So boundary point doesn't matter so much. So if that condition is true, then it turns out that this network will satisfy the 2-point condition. And the way to kind of think of it is that, you know, when h grows, you are going higher. So h is like height. And when h goes lower, when h decreases, you kind of go lower. So you kind of put this graph, you put it in space, in kind of some high dimensional space, such that there's one direction where things kind of grow. And if you're at any point, there's exactly one edge where it grows, exactly one edge where it goes down. And on the other edges, you are kind of on the same level in some sense. So that means that these kind of like lattices and things that are naturally embedded in Euclidean space, they do satisfy this two-point condition if you have enough boundary points. So you need to have this also true. So the hexagonal lattice satisfies this two-point condition. You can also modify a bit. So if you remove an edge here, it still satisfies the two-point condition. But if you remove, let's say, this edge also, then this point here will only have one edge connected to it. And if it's considered an interior node, then it will not satisfy this discrete gradient condition. And actually, then you can build a set of 2 points. For example, this point and this other one here, these 2 points. And that set will not satisfy the two-point condition. So the two-point condition is a bit more general than this gradient condition, but in practice, they are pretty similar for the interesting graphs. So that's, yeah. So you need to have this kind of structure that one direction kind of grows, other direction goes down. And then there's other examples, the triangular lattice satisfies this. And you can see in the triangular lattice, so the way we formulate these equations, the connections between boundary points don't matter. But you see, this point here is connected to 2 interior nodes, but those nodes are connected together, so it's all 2-layer lattice, square layer lattice that also satisfies. So all of these kind of like very standard lattices are okay. And little perturbations to them, like removing one edge here and there. So the rest of the time, I'm going to talk a little bit about the proof, but I don't want to make it too boring. So I'll just kind of say what are kind of useful tools we can use to prove these theorems. And then if there's time and it's not too boring, I will show kind of the main idea. Like, I'm not going to go into all the details. So recall, okay, so the theorem we want to prove is that the boundary spectral data uniquely determines the structures and then also the coefficients with some assumptions. So some tools that we use for this kind of things. So first of all, there's these operators. So we define the Laplacian and the Neumann derivative. And once those are defined, okay, actually here, so you can prove like Green's formula. So here it's proven for the whole graph, but this can also work for a subgraph. So if you take like some set of vertices and then create for them like a boundary, then you can also prove these similar things. So so you can kind of start doing like standard analysis that you do in like continuous cases once you have all these definitions correctly. So there's also something important is this eigenfunction behavior. Is that so if the graph that you're looking at satisfies this two-point condition, then the eigenfunctions of this Schrödinger equation, this discrete Schrödinger equation, cannot have both u is equal to 0 and Neumann derivative of u is equal to 0 on the boundary. However, if you look at arbitrary graph, you can construct examples where the eigenfunctions hold Cauchy data, so meaning both u and normal derivative of u vanish on the boundary. So this two-point condition is also then related to kind of doing some type of like unique continuation for solutions of PDEs. So without it, if you don't have any restrictions, you cannot even do unique continuation in any meaningful way. And then this is just this last thing is that even though I'm talking about the spectral problem, this will also solve the Neumann to Dirichlet inverse problem, meaning that if you are given the Neumann to Dirichlet operator on the boundary of this type of graph, meaning that you can set, let's say, the Neumann data of a function, and then the function solves this Schrödinger equation on the interior, and then you measure the Dirichlet data of the solution, and you're given the total, value and domain of this operator. Then from that, you can deduce the spectral data, and vice versa. From the spectral data, you can deduce the Neumann to Dirichlet operator, meaning that if we solve the boundary spectral problem, we also solve this Neumann to Dirichlet problem. And yeah. Okay. So this is meaningful because if you look at like inverse problems on networks, many of the previous results, they only consider things like trees and stuff. And whenever there's like loops, it immediately starts to be very difficult. If you look at, let's say, the Schrödinger with a potential. And I meant to say, yeah, this is the Neumann to Dirichlet, not just for one frequency, but for all frequencies. So that's a little bit different, right? Anyway, so the way to see that is just a little formula here. So if you look at the eigenvalue for this Schrödinger operator, like the eigenvalue equation on the interior, but then on the boundary, instead of having Neumann data equal to 0, you have Neumann data equal to some f. So that's why there's this f on the index there. And then you want to determine, okay, what is the Dirichlet data? Doing a little bit of simple computations, you can show this kind of formula. So the Dirichlet data of this function minus some function called WF has this kind of representation formula where you have here the lambda, which is the same here. Here you have these eigenvalues, this phi z and phi k's are eigenfunctions. So you can get this kind of representation formula for the Neumann to Dirichlet operator, where this WF is any function defined on the whole network, where the Neumann value of this function is equal to f on the boundary. And then if you look at this thing, you see that this is like a spectral representation for the Neumann to Dirichlet operator, and the poles of that operator will give you the eigen values. And then if you want to figure out the boundary values of this like eigenfunctions, you will get by looking at the residues and restricting this to the boundary. So it's kind of like the similar type of proof that's done for the continuous case, but it's kind of easier because everything is like finite in some sense. And again, it really requires that you have things like correctly defined. Anyway, so the rest of the few remaining slides, I will give you some, like, what's the general idea for proving this boundary spectral unique determination? So in the proof, we're going to look at the wave equation. So we are going to define how waves behave over time. Since space is discrete, we also will make time discrete. So here we look at like a formal wave equation, but this dt is going to be a discrete version. So t goes from 0, 1, 2, 3, 4, etc. So this just means that it's ux t plus 1, I think minus 2 of ux t plus 1 ux t minus 1, right? And then you have this Schrödinger part here. Then, since we're looking at Neumann eigenfunctions, we also want the waves to satisfy the same condition. So you put Neumann data is 0 on the boundary. And then for initial data, we put that the initial jump is 0. So the first 2 time step, it kind of stays constant. And then we put the initial value. So for any function w of x, it has to be, you know, so w has to also satisfy this Neumann condition. So any of these, any function w like this, you can solve this equation. There's a unique solution, and you just literally do it by seeing how to update this by looking at this dt squared here, dtt there. So after this, you can define how waves travel. And once you look at how waves travel, you can use the spectral data to determine several things. So you can determine the boundary values of this type of wave. So if you know the Fourier coefficients for this w, you can calculate the boundary value of this function at any time point. You can also calculate inner products of this function with w0. Where you know, w0 is any function that can be an initial value, but you have to know its Fourier coefficients. And here, let me remind you that the Fourier coefficient is just the L2 inner product with these Neumann eigen values. So it's the product of their values, and then you multiply by the weight vector here. And we do everything real, so there's no like complex conjugates here. Okay. And then how do we do the final proof? I have a couple more minutes still. So you look at very special initial values for that equation. So you look at the initial values. So you pick some point x0 inside the network on the interior, and then you define an initial value such that on the interior it's equal to the Kronecker delta of x. So it has value 1 at this point, value 0 everywhere else inside. And then on the boundary, you just continue it so that it satisfies the Neumann condition. For example, if this x0 is connected to the boundary, then you might have to, you need to put the corresponding boundary point to be 1, for example. So then you define this sets A0. So it's the set of all initial values W, which are supported at a single point on the interior. So all of these initial values of this form. And then it's a pretty complicated proof. You have to show that there exists some kind of basis in some kind of abstract high-dimensional but finite-dimensional space. You can show that the boundary spectral data determines the Fourier coefficients of every element of this A0. So in other words, this set is determined by your boundary spectral data. And that means that, you know, you can identify each of these initial values of this form with some boundary points. So you can kind of generate all the interior points. But then in addition to that, you need to know when points are connected. So we can prove this kind of lemma. So we have the graph, and we have 2 interior points, x and y. Then x is connected to y if and only if the first time when this kind of condition is true is equal to 2. So what you do is you look at this initial value where it's 1 at y and 0 everywhere else on the inside. And then you create a wave which starts at point x. So it has 1 at x and 0 everywhere else inside. And then you let the wave start to propagate. And it has to, so this wave has to propagate all the way to y exactly 2 steps later. And then that will tell that those two are connected. And then after this, we can we can identify the points, and then we can identify the connections, because we can calculate all of these solutions and these inner products with the boundary spectral data. So that gives you the topology. Yes. I will go a little bit over time, just very briefly, to show the idea how to get these coefficients. So if you want to find the coefficients, the way you do is the following. So let's say in this first case where the vertex potential is known, and we want to determine the edge potential. What we do is we again look at these kind of Kronecker delta type initial waves, and on one of them we apply this Schrödinger operator. Then just calculating what happens here, you just calculate what happens if you put this delta into this operator. You write the definition of the operator and simplify. You get this kind of formula here. It doesn't really matter what form it is, it's just this type. So we know that the left-hand side is uniquely determined by the boundary spectral data, because these Kronecker type of initial waves were determined. Then they are eigenfunctions of this operator, so you just multiply by the eigenvalue, and then you can calculate the inner products. So the left-hand side is uniquely determined. And then on the right-hand side, by definition of this initial wave, you know that this Wy evaluated at y is just 1. And this Wx evaluated at p is going to be 1 when p is equal to x, and 0 otherwise. So then actually what you have here is g of y and x. So that means that you have determined uniquely this edge condition here. And then you gotta do some similar tricks for the other situations. It's nothing too complicated, but you have to kind of invent it, the way to do it. Like once you know it, it's easy. And yeah, thank you for the attention, and sorry for going a few minutes over time.